Okay, what is meant by specific heat capacity? Now let's just say I've forgotten, but I'm really good at memorising equations, and you should all learn all of the equations, because when you get a question like this and you get stuck for a definition, all you do is go, well, I know that energy equals specific heat capacity times by the mass, and that's going to be in kilograms, and this is going to be in joules, times by the change in temperature. Okay, so I know that how hard it is to heat up times by how heavy it is times by how much I want to heat it up by. That will tell me how much energy I need to put in order to get that change in temperature. Okay, so then I rearrange it to tell me what SHC is. So SHC, specific heat capacity, equals energy divided by mass times, and this will be in Kelvin. So specific heat capacity is joules per kilogram Kelvin. You can do it that way, or you could say it is how much energy needs to be put in of a certain amount of mass. So the other way that they write this is that they say, you could argue you can put in ones, is the other way of doing it. So you'd say that the specific heat capacity is the amount of energy needed to heat 1 kilogram by 1 Kelvin. If you put degrees Celsius, that's fine. Amount of energy, and that'll be in joules, needed to heat 1 kilogram by 1 Kelvin. That's the other way of writing down what I've said there. We'll check the mark scheme and see which way was right. Okay, so energy transferred, so E equals SHC times by mass times by delta T. I'm told that I'm going from 900 and placing it in cold water. The final temperature right after placing cold water is 50, so I'm going with so that's 900 minus 50, because that's my change in temperature. Steel has a mass of 20 kilograms, and steel has an SHC of 420. So 420 times 20 times 850. Again, I need the calculator. Huge number. 7140000. Let's just check my units. Yep, they're all good. They're all good. They're all good, so I don't need to worry. No need for unit conversion. The temperature of the steel rod eventually returns to room temperature. Compare the movements and energy of the particles in the steel rod and in the air at room temperature. Weird. What a funny question. The temperature of the steel rod eventually returns to room temperature. Compare the movement and energies of the particles in the steel rod and the room to air temperature. Now this is a really hard question. So they're at the same temperature, total energy will be the same. And the total energy is made up of two different things. It's made up of the potential energy and the kinetic energy. So the kinetic energy of the air will be greater because it's gas, so it's moving faster. Which means that the internal energy, the potential energy, same total internal energy. And this one will say that which means that the potential energy of steel must be greater. That's a horrible question. If anyone gets 3 marks, I'd be amazed. When the steel rod is being quenched, the temperature of the water raises to 50 degrees. After a few hours, the water cools down to room temperature. Some of the cooling of the water is due to evaporation. Explain in terms of particles how evaporation causes the water to cool. And that is a much nicer question for 4 marks. Okay, so the particles with the greatest stop. The particles in the liquid have a range of kinetic energies. So that's one of the things about liquids. Some of the particles have very small amounts of kinetic energy, some have very fast amounts of kinetic energy, large amounts of kinetic energy. That's because they're banging into each other randomly. And it's like when you break, when you're playing snooker or pool and you hit all the red balls, some of them will go off faster than others just because they bumped into others at certain angles. So randomly, some will be going faster and some will be going slower. Well, it's the same in a liquid. Some will be going faster, some will be going slower. So you can have a range to start with. That's my first point. My second point is the fastest particles escape because they have enough energy to overcome the intermolecular bonds or forces, whichever you prefer. Forces. So that's the forces between the molecules. This means that the average kinetic energy of the particles that are left behind is lower KE gives a lower temperature. Okay, so Particles in the liquid have a range of kinetic energies. The fastest particles escape because they have enough energy to overcome the intermolecular forces that hold them in that liquid. This means that the average kinetic energy of the particles that are left behind is lower. Lower Ke gives a lower temperature.